Swayam Prabha. Digital India. Educated India.
All right. So, welcome back. We are in this course on analysis and design of rigid pavements. I hope all of you enjoyed the first lecture. In the first lecture, we talked briefly about different types of roads, different types of pavements. We differentiate between rigid pavements and flexible pavements. And we talked about when you would use rigid pavements, when you would use flexible pavements, advantages, disadvantages, etc. Now, one little piece of homework which I gave, and I hope some of you took the time to do it, is to actually go out on the road, go buy something for your parents, go to the shop, and see the type of road that you have. Try to identify, do you have flexible pavements? Do you have rigid pavements? Chances are most of you have only identified flexible pavements in local roads, but many of you may have also seen rigid pavements. Now, when you saw rigid pavements, you might have noticed certain peculiar features, certain ways by which you know pavement is a rigid pavement or not. The purpose of today's lecture, which is lecture 2 within module 1, is to talk about the types and components of various rigid pavements. I am Professor Shobhan Sen. I am an assistant professor in IIT GANDHINAGAR, and welcome to lecture 2 of our series on analysis and design of rigid pavements. In today's lecture, our learning goals are going to be as follows. At the end of this lecture, I expect all of you will be able to list the components of a rigid pavement. And through those components, when you go out in the road next time, which I hope you do again, you will be able to clearly identify whether a road is a rigid pavement or a flexible pavement. And you'll be able to differentiate between the features that actually make a road a rigid pavement and those that make a road a flexible pavement. Secondly, we will also talk about the different types of rigid pavements and we learn to differentiate between them. Now, on the face of it, it's a little difficult for a lay person to actually identify the different types. But of course, we are not lay people. All of us are engineers or are going to become engineers. So we're going to go into a little more detail on the engineering aspects of the different types of rigid pavements, what makes them different, what are the pros and cons of them, and in particular, what are we going to focus on in the rest of the series of lectures. All right, so just as a reminder, what we talked about last time, primarily there are 4 types of pavements which you'll find, although strictly speaking, one of them is not really a pavement in the traditional sense, that being unpaved roads. So unpaved roads are roads which do not have a paved surface or a surface which can carry any amount of tension. And those are generally earthen roads, little paths which are made. They are meant to be temporary, and largely in India, since Pradhan Mantri Gram Sadak Yojana and other such initiatives, the percentage of major roads which carry a fair amount of traffic which are unpaved has gone to an extremely small number. So I mentioned unpaved roads because, well, in many parts of the world, they're still there, and they are historically been an important aspect of roads in India, but increasingly they're less important. The 2 important types of roads we talked about was flexible pavements and rigid pavements, where I mentioned the basic difference is that the surface of the flexible pavement is made of a composite material, which is called bituminous concrete or asphalt concrete, and the surface of a rigid pavement is made of another composite material, which we call Portland cement concrete or just cement concrete in short. Sometimes in India, colloquially, people just call these cement roads. Of course, all of you are civil engineers, so you know that cement roads are not the same as concrete, as cement is not the same as concrete. So the correct term is either cement concrete roads, Portland cement concrete roads, PCC roads, or more generally, rigid pavements. And then there was a 4th type, which was called composite pavements. So for composite pavements, I had pointed out that they are large. They consist of both asphalt and rigid pavement components. So there is a layer of asphalt concrete and there is a layer of PCC. Where the layers are depends on the type of road. These are largely used for rehabilitation sort of projects. When you have an existing road that has essentially reached the end of its service life and some rehabilitation has been done to raise its service life or increase its service life, that's when we use composite pavements. You don't find too many of these in India as of now because we are still at the stage of building more roads. But I'm very sure that within your lifetime, we will reach a point where a large amount of rehabilitation will happen where you'll need more composite pavements. But the primary aim of this entire course is to talk about rigid pavements. So let's recap on what are the different layers in rigid pavements. So rigid pavements are a multi-layered system. At a bare minimum, rigid pavements will consist of two layers. So all pavements consist of the bottommost layer, which we call the subgrade layer. Now, the subgrade is technically a semi-infinite layer, which means that it has no specific thickness. Sometimes it is assumed that the top 500 millimeters is what we're talking about when we're talking about a subgrade. But in practice, there is no limit or there's no thickness as such of the subgrade, at least not comparable to the thickness of the other layers. The subgrade is either the natural soil, if the soil is strong enough, or it can be some amount of prepared soil, it can be some amount of stabilized soil, depending on what the application is. So the bottommost layer, whether it's rigid pavement or flexible pavement, is the subgrade. Now, on top of that, we could have maybe just one layer, and that layer would be the surface course. And that surface course for rigid pavements would consist of Portland cement concrete. Now, this is perfectly fine. As we talked about, and as we shall see later in our analysis, load transfer in rigid pavements happens through the mechanism of flexure or bending, which means that the slab itself is undergoing some amount of bending. And so the load transfer to the subgrade, because eventually all load is transferred to the subgrade, load transfer to the subgrade is primarily happening at the supports which are provided at the ends. And so the large majority of the load is essentially taken by the surface course itself. So in terms of load transfer, it is perfectly valid to have this kind of a structure where you have the concrete slab or the PCC slab sitting on top of the subgrade. This particular type has a name which we call a slab on grade. Grade here refers to subgrade. So a slab on grade pavement is where you just have your rigid pavement slab on top of the subgrade. Again, this is fine, but in practice, this is not what we see. The reason is as follows. When we want to construct the surface course of a rigid pavement, we generally have to bring some heavy equipment in. That equipment, it depends on how you're constructing it, but it could be a slip form paver, which is a fast way of constructing it, or it could be a large truck of concrete, which is just pouring concrete, which we call fixed form paving. So whether you're doing slip form paving or fixed form paving, you have to have a fairly large truck and a fairly heavy amount of equipment, which is coming and standing on the subgrade. That can lead to some amount of rutting and some amount of deformation in the subgrade, which then affects the concrete layer itself. So what we need when we are constructing a concrete layer is a stable platform. Let me write that down. We need a stable platform, not for load transfer, because the majority of the load transfer is taking place through flexure anyway. But we need a stable platform in order to provide a stable construction platform for the equipment which is needed to lay the surface course. And so generally above the surface course, we usually also have a base course. And this base course, different types of base courses exist. This could be just an aggregate base course. It could be what is called a CPB, which is a cement treated base. That is basically when you take an aggregate layer, when you take some amount of existing soil or aggregates and you mix it with cement and turn it into a more stabilized material, which is called a cement treated base, and you can put that as a layer below that. It depends what kind of road you're building, what the local practices, etc. But generally, every rigid pavement must have a base layer, not for load transfer, but to provide a stable surface, a stable platform for construction. It does participate in load transfer. We have to consider it in our analysis and design. But since a majority of the load transfer is taken by the surface layer, it's basically meant to provide a construction platform. Now, again, depending on the type of road, depending on how heavy the equipment is, depending on the cost of various materials, you may also need a sub-base layer. So the surface layer might consist of a surface course. Below that, you generally always have a base course. You may also need a sub-base course, which is almost always an aggregate course. It consists of inferior material as compared to a base course. And that basically depends on how thick a layer you want and how stable a construction platform you want. So sub-base course is optional. You have it sometimes, you don't have it other times. Base course almost always. And then the base course is providing the platform on top of the subgrade. And on top of that, the concrete layer is laid. So that, in short, is the different layers in a rigid pavement. Needless to say, you can understand here then that a rigid pavement is a multi-layered system. So when we get to module 2 and 3, when we start analyzing pavements, we have to take this aspect into account. Initially, we will not, using some initial theories related to Westergaard's theory, we will not take into account that we have multi-layered pavements, and then we'll see how those theories can be modified to account for the fact that they are multi-layered. Okay, so let's talk about each of these layers a little bit, what they're made of, what their purpose is, what their properties are. The most important, of course, is the surface course. So the surface course, as I mentioned, is made of Portland cement concrete. So Portland cement concrete is a composite. It consists of cement plus aggregates plus other components. Those other components are admixtures. They could be fibers. Within admixtures, you can have mineral admixtures, chemical admixtures, etc. We'll talk more about that in the next lecture. But the surface course is made of Portland cement concrete. Now, the primary purpose of having the surface course is to resist loads. Loads on rigid pavements, and on all pavements actually, are of two distinct types which interact with each other. One is vehicular loads, that's obviously the actual truck or car or the heavy vehicle which is driving on the road and which is creating some amount of stresses. But then you also have climate effects, and climate can be related to two things: moisture as well as temperature. So even if you don't have any traffic on the road, I don't know why you would build such a road, but for the sake of argument, if you had a road which doesn't have any traffic on it, you would still have the effect of climate load. And so we have to consider both vehicular and climatic load. And the surface course for a rigid pavement is the primary course which is going to sustain these two types of loads. When we talk about the desired properties of a surface course, obviously the most important thing that we think about is strength. So I assume all of you have some background in civil engineering. So we know that we describe concrete or we design concrete based on some target strength. So you have M30, M40, M50, so on. We have different types of concrete, and generally in structural engineering, the primary concern is the strength of the concrete. Now, in transportation engineering, pavement engineering, and rigid pavements in particular, we are also concerned about strength of the concrete. And a lot of our analysis is built on top of the compressive strength of concrete. But the difference between buildings and roads is roads are by definition subjected to climate conditions, and they are expected to last a very long time. Therefore, we have to take into account not just the strength of the concrete, but also the durability of the concrete. It's not enough if you're able to get a high strength, say M40 or M50, in the first month, in the first year, in the first 2 years off the road. We must make sure that the surface course is able to sustain that amount of strength, not for 10 years, but 30, 50, maybe even longer than that. So both strength and durability are important for the surface course. And when we try to design the concrete for the surface course, we have to take both these issues into account. Now, in addition to the above, the surface course can consist of two more components. I'll do the second one first, which is fiber reinforcement. So fiber reinforcement, so you have a surface layer over here. And typically, as we'll talk about in subsequent lectures, we expect some amount of cracking to take place. And there are different types of cracking, which we'll talk about 2 lectures from now. But there is different types of cracking, but we expect some amount of cracking to take place. The purpose of adding fibers to the concrete in this case is to hold those cracks together. That is, this crack width, as long as the crack width is very small, and this is something you can also try if you go out on a rigid pavement, as long as the crack width is very small, you can basically drive very comfortably and very safely over it. The purpose of adding fiber reinforcement is try to hold that crack width together, to try to keep the cracks as close as possible so that you can still have a safe and comfortable ride. So in some cases, not always, in some cases, we also add fiber reinforcement, and we'll have towards the very end of our lectures in lecture 40, we'll talk about how we can design for fiber reinforced concrete for rigid pavements. But fiber reinforcement is an option. It's not very widely used, but it is becoming increasingly popular. The second thing we add is steel. Now, I should point out when I say steel here, I don't mean steel fibers. I didn't talk about what type of fibers, and we'll talk about that later on in later lectures. But by steel, I basically mean steel bars, what many of us in at least the Hindi-speaking states, what we call saria. These steel bars, we know they're used in structural engineering. So if any of you have taken a course on reinforced concrete design, you know very well that you have primary reinforcement, secondary reinforcement, etc. Steel is also used in rigid pavements. But when we use it in rigid pavements, we give it two particular names depending on what their function is. We'll talk a little more about the function in subsequent slides. But we can have dowels and we can have tie bars, or sometimes just called ties. These have two distinct purposes, but basically they're both steel bars. That is, when I say that we have steel and concrete, I'm talking about these steel bars, not steel reinforcement. Most cases for rigid pavements, we do have steel. What differs between different types of pavements is the amount of steel and the placement of the steel. But generally, we do also have steel. By the way, in the previous lecture, I had talked about the fact that concrete pavements have a high initial cost, and I had pinpointed the initial cost to the fact that cement is a more expensive product than bitumen, which is a byproduct of fractional distillation of crude oil. I should add now that I've given this background, an additional initial cost to constructing rigid pavements actually comes from steel. Steel is very expensive as a product, and a large volume or large quantity of steel is used in constructing rigid pavements. So that's one more thing that adds to the cost. But as we shall see, it also adds to the durability and strength of the pavement over time. And that's why we use it. Now, below the surface course, we have a base course. As I said a couple of minutes ago, the purpose of having the base course is to provide a stable construction platform. It does participate in load transfer to an extent, but that is not its primary purpose. The purpose is to provide a stable construction platform. It could be an aggregate layer, and in many cases, it is an aggregate layer. But in many cases, particularly in India for highways and expressways, it also could be a cement stabilized layer. As a recap, what is cement stabilized? So basically, you have some soil, you have some aggregates, and to that we add cement, but we add cement in a lower quantity of cement and a lower amount of water. So we don't get as much strength, but we get some type of stabilized layer which is not as strong as the surface course, and that we call as a cement stabilized layer. Now, a CPB or an aggregate layer, it cannot actually resist a very large amount of load. In other words, their tensile strength or their load capacity is not very high, particularly if you compare it to the surface course, which is made of PCC. But as I mentioned, they don't need to have a high load resistance because a vast majority of the load is taken by the surface course. Instead, the main purpose of having a base course is to provide a stable construction platform. In many cases in India, we also have the practice of adding what is called a bond breaker. So we have a surface course over here, as I'm drawing over here, we have a surface course, and below that we can have a base course. And it is a practice to put a PVC sheet or a plastic sheet in between the two. The basic idea for doing this is to keep moisture out of the base in case the base is made of an aggregate layer, or if the base is a cement treated base and you have some amount of cracking developing in the base, we don't want that cracking to propagate to the surface layer. So it's meant to either protect the base layer or protect the surface layer, depending on what type of layer you have. So many times we do have this little plastic sheet which is kept in between. This is called a bond breaker because it ensures that the surface course and the base course do not have any bond. Bonding we'll talk about when we get to module 3, when we have unbonded, bonded, and Trotsky bonding layers. We'll talk a little bit more about that. But just to give you an understanding of what it means physically to have a plastic sheet, basically you have structurally separated the surface layer from the base layer. So now they're resisting load in completely different ways. And that's the net effect of having a bond breaker. The purpose is more functional. It is to prevent any distress or moisture from reaching either the base layer from the surface or from the surface to the base layer. Sub-base course, as I mentioned, is more of an optional course. It is almost always an aggregate layer. It also participates in providing a stable construction platform. So it provides additional support for construction if necessary. Many times that is the case when the soil is relatively weak and either you have a fairly thick base layer, which is a cement treated base, or if you want to lower the cost, you may have part of the base layer which is cement treated and then an aggregate sublayer of inferior material below that. So we could have a surface layer, which I'm drawing over here. We could have a base layer. And then if our subgrade is rather weak and we need a more stable platform for construction, then we might go in for an aggregate subbase layer. Sometimes this aggregate subbase is shown with the symbol GSB, which stands for granular subbase. So aggregate and granular, they're sort of synonymous words. And even in my lectures, I will use them more or less synonymously. In many cases, they may or may not be present. So it depends on the particular road and the particular type of construction which is going on for the road. And finally, we reach the layer which is the subgrade layer. Now, this is common between rigid and flexible pavement because it's the last layer and it consists of soil. If the subgrade has sufficient CBR, I'll define CBR in a second, but if it has sufficient strength which is measured by CBR in a way, then you can just use the natural soil, which is you have the existing road. You might have to clear some amount of debris, some amount of the topsoil, but you can essentially start building the base layer right on top of the subgrade if it's sufficiently strong. Sometimes you do not have adequate strength in the subgrade layer. In those situations, we have to do some amount of stabilization. So you can have cement treated subbase, you can have cement treated subgrade, you can have asphalt treatment, you can have subgrade replacement. There are many options for subgrade stabilization. So now, what is CBR? We'll talk a little more about this in the next lecture, but CBR, as many of you may have taken if you've taken a transportation engineering course, stands for California Bearing Ratio. So it's actually not used all that widely currently in pavement design analysis, as you will see in subsequent lectures. But it is, for historic reasons, it's almost 100 years old as a measure. It is an empirical measure of the strength of a layer. I mean, it's almost always used only for a subgrade layer. So it's some kind of empirical measure of strength. We'll talk subsequently in later lectures what exactly that means and how we can quantify it in more mechanistic terms. But it's an empirical measure of strength. So if the CBR is low typically means something of the order of maybe 3% or less. If it's low, then we have to do some kind of treatment to the subgrade. If it's high, 3 to 5% or perhaps even more, then we might be just able to use the natural soil. Of course, removing a little bit of the top surface and doing some amount of grading. The most important thing in terms of durability. So CBR talks about strength, but strength alone is not important. One of the most important things for subgrade to consider is moisture susceptibility. Now, what can happen is if I have a rigid pavement, which I'm drawing over here, so we have these multiple layers, there are ways, and we'll talk about those in a couple of slides, but there are ways by which moisture, for example, from rain, or it could be from the water table, moisture might be able to ingress into the subgrade layer. If that happens and the material of the subgrade is highly susceptible to moisture, then you'll have a subgrade which becomes extremely weak, and that is going to almost immediately set off a chain of distresses in the surface course. So it will be felt very strongly by drivers and it will be felt relatively quickly. So one of the most important things when looking at subgrade and the type of subgrade, it's not just the CBR, but also the moisture susceptibility. And if you happen to have a fairly moisture susceptible soil, then there are ways by which some amount of treatment has to be done. That's not the most important aspect of this class, but it's something to keep in mind, which is part of the analysis and design of rigid pavements. Okay, so now that you understand the different types of layers and different types of materials, let's go into what are the different types of rigid pavements. Now, all the rigid pavements have the same layers. That is, you can have a surface layer which is made of PCC. Then you can have, generally you always have a base layer. You might have a granular subbase, and below that you'll have a subgrade. So generally all the types of rigid pavements follow this basic scheme. The difference in the type of rigid pavements, however, is in terms of what happens in the surface course. What is the nature of the surface course? In particular, what type of steel is used in the surface course and how the surface course is constructed. So based on that distinction for the surface course, we have 4 different types of pavements. They are as follows. Jointed plain concrete pavements, or JPCP. This is the most widely used type of rigid pavement. Chances are, if you go on the highway or if you have any concrete pavement nearby, more likely than not, this is going to be a JPCP pavement. By far, it is the most widely used type of concrete pavement or rigid pavement. The second one, which is actually quite rarely used today, is called jointed reinforced concrete pavement, JRCP. So don't get confused with the terminology. It's just a little line which is the difference between the two. JPCP versus JRCP. JPCP is the most commonly used. JRCP is actually very rarely used, and you'll have a tough time actually finding an example of JRCP in practice. There is a third type called continuously reinforced concrete pavements, CRCP. It is used more often. It is extremely expensive for reasons which we'll talk about in a couple of slides. But it is often very important to be used for highways or expressways. And sometimes you'll also see it being used on runways at airports. So CRCP is extremely expensive, but it can be used. It can be a good option to use for the highways or expressways which are carrying very heavy loads. And then you have a third type which is used rarely, although it's used more in airport pavements than in highways, which is pre-stressed concrete pavements, PCPs. And as the name suggests, it consists of some amount of pre-stressed blocks, which we'll talk about in the coming slides. So broadly, these are the 4 types of pavements. What I'll do in subsequent slides is I'll go into details on what these are, what is the difference between these different types of pavements. But keep in mind, as far as this class goes, we will primarily focus our energy on JPCP, a little bit on CRCP. JRCP and PCP, beyond today's lecture, we are not really going to look at all that much. Okay, so let's jump right in. I thought we'll start with the simplest one, which is JRCP. JRCP, which is jointed reinforced concrete pavements. So here we have an example of jointed reinforced concrete pavements. I'm sorry, there is a slight typo in the slide. This should be jointed plain concrete pavements, right? So JPCP. We'll start with JPCP, which is the most common type. Now, the name actually tells you quite a lot. Jointed. So, again, if you actually go out and look at a rigid pavements, you will see it is as follows. Of course, you have a layer of concrete, but within the layer of concrete, you'll see the concrete itself has been cut into slabs. And the location at which they are cut, that gap which we create in between, that is called a joint. Now, why do we have joints? Some of you may know that they're to allow expansion, contraction, but there are actually other reasons for having joints. We'll talk about that subsequently today as well as later in the lecture. But when you have JPCP, which again is the most common type of rigid pavements, you do have joints. So these joints are typically cut after casting, which is first you cast the pavement, you cast the concrete, and then you get a saw and you cut them. In some cases, it is possible to put some concrete or to put some aluminum or glass slats. So you kind of create a form and then you cast concrete on them. That's usually used for lower volume roads which are carrying less traffic. Now, the reason we have joints is because they affect the magnitude of stresses developed. We'll talk about in later lectures that rigid pavement performance is primarily determined by the tensile bending stresses which are developed inside the slab. And as you decrease the size of the slab, the stress in the slab also decreases. So obviously, if the stress is lowered, we can expect better performance. That's kind of intuitive as a civil engineer. And so joints affect the magnitude of the stresses which are developed. And that's the primary reason that we have joints. If we have smaller joint spacing, which is the joints are spaced at a smaller distance, that's equivalent to saying that you have a smaller size slab. So smaller joint spacing, smaller size slab, these mean the same thing. Then you will have lower stresses. I'm saying this right now qualitatively. Once we get into module 2 and we start looking at some more detailed analysis related to Westergaard's theory and subsequent improvements, we will actually formally see data which has proven this exact thing. But generally, smaller joint spacing or smaller slabs implies that you have lower stresses. And so ideally, when we have a pavement, we do also want to put a fair number of joints inside the pavement. Okay, that sounds good. But then what is the flip side? What is the cost of making the joint? As I said, first we pour the concrete, and then we have to go back and saw the joints into the concrete. That is an expensive process. Sawing is a manual process. It requires labor, and it requires somewhat skilled labor because, using a saw and being able to push it and put the right amount of force is something that requires a fair amount of skill. So sawing is a time-consuming and labor-intensive process. So in theory, in order to decrease stresses, you would like joints to be as closely spaced as possible. In other words, you would like to have very small slabs. However, in practice, you don't want extremely small slabs because then you'll be doing so much saw cutting that it becomes uneconomical to actually construct the road. So we need to strike a balance between having very small slabs, in other words, very closely spaced joints, and very largely spaced joints, which will develop too much stress. So between economics and performance, we have to find some type of a balance. So a jointed plain concrete pavement is one where we have a plain concrete. In other words, there's no steel inside it. So the word plain over here refers to the fact that there is no steel inside the pavement. We don't have any steel, although we do have steel at one spot, which we'll talk about in a second. We don't have any steel, hence the term plain, and we have purposely sawed joints in it, hence the term jointed. Jointed plain concrete pavements. Now, a little bit more on joints. So typically the joint spacing for JPCP is going to be 3.5 to 4.5 meters. Again, the joint spacing is a function, it's an optimization between having very small joints and therefore having low stress versus having very large joints and therefore making it cheaper and more economical to construct, but with higher stresses. So we trade off between these two, and in practice, the joint spacing or the width of the slab is 3.5 to 4.5 meters. When you have a JPCP pavement, again, this should be JPCP, then the typical slab thickness is 150 to 400 mm. In many cases, the 150 is probably the lowest limit, and generally it's too low for any road with a fair amount of traffic. It can be sometimes used as an overlay over an existing road. So I'm putting 150 there, but generally it's not too common to see a 150 mm thick layer. You can go to 400, and that's typically what you will see in a fairly well-used highway with a fair amount of volume. But you can also actually go higher than 400, and that you might see in airport runways, where we have significantly heavy loads. There you can start seeing concrete sections which are going above 400 mm. Thinner slabs, as I said, could be on composite pavements. It's difficult to have thinner slabs. They essentially are too weak. They develop too much stresses. So thinner slabs may be used as a composite with an existing pavement, and thicker slab may be used on runways. Okay. Now, the important thing to understand for joints. So we first construct the concrete layer, and then the joint is sawed inside of that. We generally saw it up to halfway. So we join, if h is the thickness of the layer, the joint is typically sawed to a distance of h over 2, and then you have some crack which is formed underneath. The important thing to understand is the joint is basically a hole in the concrete that you have purposely created. Now, I talked a couple of slides ago that moisture is a big problem for the base layer as well as the sub-base layer. And moisture can reach from the surface course, from rain, all the way down to the base and the sub-base and the subgrade layer. The most important and the most common way it reaches there is through joints. So when you've cut a joint, you've basically created a hole. And that hole provides a relatively easy path for moisture to enter the base, sub-base, and subgrade layers, and that can weaken the entire pavement. So it is very important to not just saw the joints, but also properly clean and seal them. And sealing basically ensures that they are waterproof or that moisture can't go through them. Typically, we use some type of a polymer-based sealant, and there are a variety of products which we won't talk about, but they are not the same as bitumen, but they are also some type of byproduct of fractional distillation. So it's some type of bituminous-like material which can be used as a sealant, and the sealant is then applied into the joint in order to make the joint waterproof. Okay, so now what I want to do is I want to go through each of these 4 different types of pavements, which is JPCP, JRCP, CRCP, and PCP, and give you the difference between them. I mean, the difference is basically only in the surface course and how they're constructed, but that difference makes quite a lot of difference in terms of performance, construction, and cost. The first type, which I mentioned, is the single most common type of pavement that you'll encounter, is jointed plain concrete pavement, which we just write as JPCP. And so in literature, you'll just find it called JPCP everywhere. All right, so here is the general idea. It consists, the name tells you quite a lot. It is plain. So plain concrete is the opposite of reinforced concrete. Reinforced concrete is where you have steel. So plain concrete doesn't have steel. By the way, it's not to say that JPCP doesn't have steel. Actually, JPCP has quite a lot of steel. We'll talk about that in a second. But mostly JPCP doesn't have steel by area. And so that's why we call it plain. And the other term here is jointed. So what does that mean? So let's consider how these are constructed. Generally, mainly for highways. So for local roads, it might be a little bit different, but for highways, what happens is you would lay a large amount of concrete. So over a fairly large area, you pour concrete to a particular thickness, to a particular grading, etc. And while it's setting, it has to be sawed. So you actually bring in this diamond tip saw, and it has to be sawed at particular lengths. When you saw it, then you are basically cutting off the monolithic concrete into individual slabs. And that gap which you have created between them through sawing is called joints. So jointed plain concrete pavements are concrete pavements which are plain. So within each slab, you don't have any steel. And they are jointed. In other words, you have certain joints which in turn create these individual slabs. Now, why do we have joints? In theory, you don't have to have joints. You can have a concrete which is a continuous concrete. It doesn't have joints. Indeed, if you are sitting inside a building right now which has a concrete slab for a floor or a ceiling, you are looking at an unjointed concrete slab. So why do we need to have slabs? The main reason why we have slabs in JPCP is because of stresses. So where a large slab accumulates shows a very high concentration of stress or a very high magnitude of stress under a given load as compared to a shorter slabs. So in short, shorter slabs, which is equivalent to saying smaller joint spacing. So either I can have a smaller joint spacing, or I can have a shorter slab width. Both of them mean exactly the same thing. So a shorter slab or a slab with lower joint spacing has lower stresses. That is the main reason why we put joints in the first place. Okay, but then we could go to another extreme and say that, well, if short slabs have less stress, then maybe our slab should be extremely short. We should have a very, very regular series of joints. Well, the problem is that leads to slower construction. As I mentioned, the way these are typically constructed, at least for highways, is that you have to pour the concrete and then you have to have some amount of trained labor who know how to use this equipment, who are going in and physically sawing the concrete, sawing the joints into the concrete. That's a costly process. It's costly because you need to have some amount of trained labor to do it. You also need to rent the appropriate equipment, and that can slow down construction quite a bit. So on one side, you would like to have short slabs to reduce the amount of stress, and when you reduce the amount of stress, you improve the performance of the pavement. On the other side, you don't want to have very short slab because it starts becoming uneconomical to construct such pavements. So we need to strike some sort of a balance between joint spacing or slab width in JPCP pavements. It has been found that the typical joint spacing from experience, which happens to work, is 3.5 to 4.5 meters. So most pavements in India, most JPCP pavements in India, if you go out on the road and if you happen to live near a JPCP pavement and you actually measure it, of course, be careful of traffic, etc. But if you actually go out and measure it, you'll see that they are roughly 3.5 to 4.5 meters in length. That is what's been found to be an economical slab size, and which also performs reasonably good performance when the slab is about 150 to 400 thick. So this is the typical range. We can get to higher values also. 150 thickness of the slab is actually relatively thin. If you have a slab on grade or even a JPCP pavement which is on top of a subgrade, or on top of a base layer which is on top of a subgrade, you generally will not have 150 150 is a fairly thin pavement. It is used, for example, on composite pavement. So if we have a bonded concrete overlay, so if we have an existing asphalt layer, and on top of that, we, for the purpose of some amount of rehabilitation, we construct a JPCP section on top of it, then that is what we call a bonded concrete overlay. And in that case, because you have good bonding between these two layers, you can have a relatively thin, which is around 150 thick surface layer. But in practice, if we just have JPCP sections without considering composite pavements, then you have to typically have more than 150. You have to have 200 or higher. 400 is also relatively thick, although you can get even thicker than that. And when you start getting higher than that, that can be used, for example, on airport runways, which are carrying very heavy loads, and therefore you need to have a very thick pavement for those kind of applications. Generally, what you'll find is 200 to 300 or even 350 is the typical thickness of a JPCP section that you will observe in practice. One more thing to add, the thickness of these sections, we don't put any thickness in practice because there's a limit on what thickness we can measure in the field and what the contractor can lay. So generally we do it at every 25 to 50 So if we have 200 maybe the next available thickness is 225 or 250 depending on the contractor. So although thickness is a continuous value, when it comes to pavements, we look at it discretely in steps of either 25 or 50 That's due to constructability. Now, talking a little bit more about JPCP, as I mentioned, in JPCP, basically we have a slab. And then in a slab, we saw a joint into it. Now, the saw doesn't go through the entire thickness. If the thickness of the section of the slab is H, which I mentioned already, is 150 to 400 If the thickness is H, then the saw depth, which has to be sawed in, is typically H over 2, or it can be H over 3 in some cases. It depends on practice and type of concrete. But basically, 1/3 to halfway through the thickness is what you have to manually saw into the concrete. The remaining is expected to develop some amount of cracking along the way, and that develops sufficiently early during the life of the pavement, so that overall you have divided the two slabs. So you have one slab over here, and you have another slab over here. About halfway through the thickness, you have physically divided them by sawing a hole through it, which is a joint. And then you will develop some amount of cracking in between, which further divides the two. And that's how you create these two separate slabs in JPCP. Now, what you will notice is that when you saw a joint, you have basically created a hole in the slab. couple of slides ago, I talked about the subgrade, where a very important consideration for subgrade is moisture susceptibility of the subgrade and ingress of moisture from the surface course to the subgrade. That obviously it happens because of rain or surface runoff, but joints, since they are basically a hole on the surface, are a perfect location for moisture to enter the surface course, reach the base, subbase, and subgrade layer, and therefore degrade the entire pavement. Naturally, if you're thinking about performance, we have to do something to prevent this from happening. So it's not enough to just have joints. The joints also have to be properly cleaned and then sealed off such that they are waterproof. And that sealant is usually some type of a polymer sealant. Usually it's an asphaltic or a bituminous product. It's not the same as the binder. It also comes from fractional distillation, but it's not exactly the same thing. So some type of asphaltic or bituminous product is typically also used to seal off the joint, and that prevents ingress of moisture into the subsurface layers. This is actually an extremely important step. On their own, without sealing off the joint, the subgrade is left completely to be exposed to moisture. Within one monsoon cycle, you would have a very damaged pavement. You must seal off the joints and in order to prevent that sort of moisture damage from happening. Now, joints, in addition to reducing stress, joints also need to allow free expansion and contraction of slabs. So what that means is that when the slab is heated, as we know, when all materials are heated, they expand, and when they're cooled, they contract. So when we have a joint between these two slabs, which I'm drawing over here, then if they contract, then they must be able to freely contract without any additional stress. Similarly, when they expand, they must be able to freely expand. So there is typically a minimum required joint width, which enables this expansion and contraction to happen. These type of joints we call contraction and expansion joints. There is an additional type of joint which is called a construction joint. It's not a joint which was supposed to be there. It just happened to be there because the construction ended for that day. So that's where you finish, and next day you pick up and continue constructing from that point. So a joint which is placed for the sake of the fact that you have to stop constructing for the day is called a construction joint. And a joint which is placed on purpose, which has been sawed on purpose to allow for expansion and contraction and to allow for reducing the stresses, is called a contraction and an expansion joint. It is very important, again, that joints have to be properly cleaned and sealed to prevent any moisture ingress from coming in. Otherwise, the entire pavement can be damaged in a relatively short period of time. Okay. Now, a little bit more on JPCP. This is the last slide I have on JPCP. Again, JPCP is the most widely used type of concrete pavements, which is why I'm going into a fair amount of detail on it. Now, if you consider each individual JPCP slab, you will have a load on the slab. And in theory, the slab is bearing the load and the adjacent slab doesn't have to bear any of the load. This is a problem, however, because what happens is then you are basically using only a small part of the capacity of the overall pavement. So in the drawing I have over here, you have two slabs. The slabs are next to each other, but if you expect only the load, only the slab that the load is on to carry the entire load, you can end up having to have a fairly thick slab to resist a fair amount of stress. Whereas if somehow we could transfer a small part of the load onto the next slab, so the slab which I've shown here on the left, that is still the loaded slab. But if somehow we could allow the next slab to participate in the load transfer process, then we can end up decreasing the stress on the loaded slab, and therefore we can have a thinner slab which uses less material. That process is called load transfer, which I'll write over here. So that is called load transfer. And it is generally very common in JPCP sections. There are three mechanisms by which load transfer happens, two which happen basically all the time, and one which has to be done with some amount of thought. The first is base friction, and the second is aggregate interlock. I can explain these two by going back to this figure which I had drawn in the previous slide. So below this layer, what I have over here is I had the joint, and I told you the joint is sawed to h/2 to h/3. And then below that, we have a crack which forms. Now, this crack, imagine that this slab has been loaded and now the slab is trying to deform. Because you have a crack over here which is in aggregate interlock. So the aggregates, one side of the crack, are in contact with aggregates on the other side of the crack. When one slab is trying to move downwards, let me draw this a clean view over here. When this slab tries to move downwards, there is some amount of interlock which is happening along that crack, and that aggregate interlock is going to transfer some amount of the load from the loaded slab to the unloaded slab. Similarly, the slab is sitting on top of on top of a base layer. The base layer itself is going to have some friction. So the friction of the base layer is going, because the base layer is a continuous layer, because of the friction of the base layer, when you have some amount of load happening on this side, on the loaded side, it's automatically going to be transferred to the unloaded side because the base layer is a continuous layer. So the two simple mechanisms which are present in almost all JPCP sections are base friction and aggregate interlock. These allow for load transfer from one slab to another slab. Generally, these are not very high. And if we just depend on base friction and aggregate interlock, we are not going to have sufficient load transfer and we'll end up with having a fairly thick pavement. So there is a third transfer mechanism, which is dowel bars. So as I mentioned, the individual slabs in JPCP are plain, which means they don't have any concrete, they don't have any steel in them. But in between these slabs, we do generally put steel. And these steel are then called dowel bars when they're particularly put for the purpose of transferring load from one slab to the other in the direction of the traffic. Then we call those type of steel bars as dowel bars. Now, here is what dowel bars are doing. Again, I will draw the joint over here, but here now I have additionally put a dowel bar. Now what's happening is this slab is loaded, the slab is trying to deform. The dowel bar, on the other hand, is pressing against the adjacent slab, the unloaded slab, and transferring load through the dowel bar. So in addition to this interlock transfer as well as base transfer, now you also have dowel bar transfer, and that turns out to be the most significant mechanism for load transfer between slabs. So it is also possible to have these steel bars in the longitudinal direction. So if this is the direction of traffic, we call this the transverse direction, and the perpendicular direction is called the longitudinal direction. We could also have steel bars along the longitudinal joint. Now this is mainly meant to hold the two slabs together. It doesn't have too much of a role in terms of load transfer. In that case, those steel bars are called tie bars. So dowel bars primarily are responsible for load transfer, while tie bars are mainly present to hold the slabs together. They don't contribute as much to load transfer. Now, one last thing on dowel bars. I want you to notice in this figure where I place the dowel bar. The dowel bar is generally always placed at a depth of h/2. That is, it's placed exactly in the middle of the slab. For those of you who've taken a class in structural engineering in reinforced concrete design, this will come as a little bit of a surprise. Generally, what we understand in reinforced concrete design is that the steel is supposed to be put on the tension side. So, for example, if you have a beam, then the steel is usually put on the lower side because that's the tension side, if you have a simply supported beam. Whereas if you have a cantilever beam, then the steel is usually put on the upper side because that is the tension side on a cantilever beam. That's all correct in structural engineering. In pavement engineering, for reasons which we'll talk about in a couple of lectures from now when we talk about top-down and bottom-up cracking, but several lectures later, what we'll see is that this tension side is basic. The tension side on a JPCP slab keeps flipping between day and night. So in the day, you'll have tension at the bottom. In the night, you'll have tension at the top. So as a trade-off between these two, we put the steel in the middle. And secondly, in structural engineering, steel is participating in the load capacity of the slab. As many of you might have studied, that we take steel into account in the stress block, and we take into account when doing the design. In concrete pavements, however, the role of steel is limited to transferring the load from one slab to the other. The steel is not participating in strength. So the steel that we place on these joints, which are dowel bars, has no role in increasing the strength of JPCP. They are purely meant for load transfer. So fundamentally, steel which is used in pavement engineering is very different functionally from steel which is used in structural engineering. That's something we'll talk about in much more detail in a couple of lectures from now when we go into joints and dowels. Okay, so that was all on JPCP. The key idea in JPCP was that individual slabs are plain. They don't have any steel in them. We only place the steel at the joints. Those could be dowel bars if it's transverse joints. Those could be tie bars if it's longitudinal joints. So JRCP, jointed reinforced concrete pavements, the name should tell you what the difference is. The difference is in this word reinforced. So if JPCP, each slab was plain, which means it didn't have any steel on it, then in JRCP, each slab has some amount of steel reinforcement in it. So again, if I draw these slabs, in this case, for JPCP, we just had steel reinforcement at the joints, but with no steel reinforcement inside the slabs. In JRCP, we have steel reinforcement inside the slab also. So we have a mesh of steel which is present inside the slab. The purpose of steel here, similar to what we talked about JPCP, is not to increase the strength of the section. Steel does not participate in the as a part of the strength of the section. Instead, the purpose of the steel when we add it to JRCP is to actually hold the cracks together. So crack formation depends on the strength of the plain concrete, but the width of the crack depends on the steel content. So the purpose of the steel mesh is to reduce the crack opening width to hold the cracks together. It does not prevent cracking. That's an important difference to understand between structural engineering and pavement engineering. Now, the advantage of when you have JRCP is when you have JPCP, then crack widths tend to be long, which means we have to have shorter slabs to reduce stresses. When you have JRCP, although stresses do develop and cracks do form, the crack widths are very small, and so we can tolerate small crack widths, which means we can allow higher stresses, which means we can allow for longer joint spacing. And typically in JRCP, we can have a joint spacing of 15 meters compared to 3.5 to 4.5 meters, which we use for JPCP. Now, so it sounds like JRCP is a good option. In practice, however, it has been found to have poor performance. It is rarely used, and you would be hard pressed to actually find a JRCP section in practice. There are very few of them in the world. Instead, what is used, what you will find many examples of, is an extension of JRCP, which is called continuously reinforced concrete pavement. So reinforced here again implies the fact that you have within each slab, you have a steel reinforcement. So it's not plain slabs. But the word continuous here implies you have no joints, or in other words, you don't have any individual slabs. So in this case, you just have a continuous pavement which has a steel mesh inside of it. No joints have to be sawed inside. This is why it's called continuously reinforced concrete pavements. There are no joints present. Like JRCP, the steel reinforcement is usually 0.5 to 0.7% by area. How we do the analysis and calculations for this, we'll talk about several lectures later, towards the end of this lecture series. Here again, similar to JRCP, the important thing to understand is the steel mesh holds the crack together. As I show in the subsequent slides, CRCP actually develops a lot of cracks. Generally, if you look at a CRCP section, it will be, as I'm drawing over here, you'll have a continuous series of cracks roughly 1 meter apart. So you have a lot of cracks which form, but the cracks are held so tightly together by the steel that the opening width is very small and it's still quite comfortable to drive on. The the steel in JRCP as well as in CRCP does not prevent cracking. It is assumed not to resist any loading. It just holds the crack together. Very big distinction from structural engineering, and that's the primary difference between how concrete pavements are designed versus how structural slabs are designed. And we'll come back to this further in later lectures. So here's a picture which I got from the US Federal Highway Administration. Here they are constructing a CRCP segment. So first of all, you see over here, you have a lot of steel. These green bars, they're basically the same concrete bar, the same steel bars, but they've been coated in epoxy. That's why they're green. You have these green bars, which are steel bars. And what you can see is you do have some area where you have some splicing in between. So you have two bars and there's some overlap between them. That overlap area is called splicing. So splice. And then concrete will be poured over this. No joints have been constructed. It's just a large segment over concrete is poured over this steel. Once the concrete sets, this, as you see in the lower image over here, you'll get this continuous series of cracks which form roughly at every 1 meter apart. And that is not a problem, that is not a defect, that is a feature of CRCP. You have this continuous cracking because you don't have any joints, but the steel holds the cracks together so tightly that it does not affect ride quality. Okay. Now, it sometimes what does happen is about roughly maybe 100 meters apart. Sometimes some joints are made on purpose. They are sawed on purpose. That's largely so that we can control the pattern of cracking. So what we like is if we have cracks which are nicely spaced approximately every 1 meter apart, which are almost parallel to each other. Sometimes what happens though, the cracks are not parallel to each other. And when that happens, you can start having cracks which are going somewhat diagonal, and one crack will eventually merge with another crack, and you will have a section of the concrete which then pops off because you've basically broken it from both sides. This is what we call a punch out. And this is the main failure mechanism in CRCP. We generally don't want this to happen. So in order to prevent this type of cracking, this diagonal or Y-shaped cracking from occurring, maybe around every 100 meters apart. Again, compared to 3.5 to 4 meters for JPCP and about 15 meters for JRCP, approximately every 100 meters apart, sometimes some joints are actually sawed. And in that case, it is called active crack control. So those are placed on purpose to prevent punch outs or Y cracks. But in general, CRCP does not have any joints. There's no need to saw. So they can be constructed relatively fast. Well, that's good. That takes care of the construction issue. That takes care of the problem of having a lot of cracking. The problem is they can be extremely expensive due to the high amount of steel. The fact that you don't have joints will offset the cost a little bit. So you don't need to have the labor and the equipment to do the joints, to saw the joints. But it's still going to be extremely expensive to construct them. So CRCP is not used all that often, but there are plenty of examples around the world, including in India, where CRCP has been used. It has been found that if constructed properly, that's always a caveat which I add, if constructed properly, CRCP has shown to have exceedingly good performance with almost no maintenance required on high volume roads with heavy loads, the most difficult type of roads to actually design. Lot of heavy trucks on the roads. For such roads, it has been found that CRCP can have almost no maintenance for decades. Not 1 year, 2 years, or a couple of years, but for decades throughout, you can build it and forget it, of course, if it's constructed properly. So that is the major reason why CRCP is used at all, because its life cycle cost, besides the initial cost, there's almost no life cycle cost at all. So it's very convenient in terms of maintenance, but yes, the initial cost is extremely high. So CRCP is generally not suitable for local roads because of this high initial cost, but for major national highways or expressways, which are expected to carry very heavy loads and high volumes of heavy roads, they might be a suitable option. Okay. The last type of pavement which I want to talk about is one which is rarely used, which is pre-stressed concrete pavements. So if you recall, I mentioned one disadvantage of having rigid pavements is the long time to opening. So after you lay the concrete, after you pour the concrete, after you saw the joints, you have to wait 28 to 90 days for the concrete to reach adequate strength before you can open to traffic. That's quite a long time to wait. And in India, one issue is that many people don't respect barriers and they tend to drive on roads which have not acquired adequate strength. And so that can lead to some premature cracking. So that is a major disadvantage of using rigid pavements. Precast slabs is a modern technique to overcome that. So in this case, what you have is you basically have a precasting plant. In a precasting plant, you have a slab which you pour in the plant itself. So you are not doing the construction on the site. You have a form, and typically you can have 100 to 300 meter long, although it depends on constructability and how well you can transport such a long slab. But you can have a fairly long slab which can be cast inside a plant. Now, what does pre-stressed mean? What that generally means is what we'll do is we will have a form, as I've shown over here, and you will have these strands of steel which are placed inside that, and we will typically then apply some amount of tension to the steel. So we will pre-stress them, hence the term pre-stressed. We will pour concrete on this, allow the concrete to set, and then we will release the steel. So what's going to happen is the steel is initially put in tension. So you are pulling on the steel in tension. Once you release it, the steel is going to try to come back, and that is going to end up compressing the concrete. Hence the term pre-stress, so it's pre-compressed. These precast slabs can then be transported to the site and simply placed on the road. So the precasting process itself is done off-site, but the construction obviously has to be done on-site. So here is an example of a figure. This is on the right is what you have is an actual precasting plant. So you see a very large slab, and there's a person over here for reference, a very large slab with these steel strands added to it. Concrete is poured to it. You can have very high quality control in this case because naturally you are constructing the slab inside a plant. You can exactly control temperature, you can control mix design, you can control timing very, very accurately in the plant. So you can have very high quality control. Once the slab has been cast, it can be transported on site, simply laid, and generally you can do that overnight, and next day the road can be opened up to traffic. So the problem of having the late early opening, a long early opening time is eliminated because now the entire construction, most of the construction happens in a plant, and the actual construction on site just takes basically one night. So the advantage is you can have superior quality control, which I mentioned sits in a plant, and then you can have quick opening time. This is basically the biggest advantage is the quick opening time. But naturally, because now you actually have to construct a precast plant, that is quite expensive to actually construct a plant, maintain a plant. You have workers, you have HR managers, etc. It's quite a process to construct a plant. And then transportation of those PCP slabs is also quite an expensive process. A small little lorry is not going to cut it. You'll need fairly large equipment to actually be able to transport these PCP slabs in large volumes. So the disadvantage of having PCP pavements is that they are expensive, both because of the plant as well as due to transportation. But the advantage is that you can have superior quality control and quick opening time. Now, generally, you will not see PCP used in highway pavements. Largely, they are too expensive to use, at least at this stage in India's development, they are too expensive to use. There is one place where you'll see them used where actually shutting down the road is critical and it's very important to open it as soon as possible, and that is on airport runways. So airport runways also have to be maintained over some period of time. Of course, they're not done every day, but there is a fair amount of regular maintenance done on airport runways. Shutting down a runway is an extremely difficult process because then you create a lot of chaos in interconnected and international flight schedules. So if you have to shut down, the runways are shut down for some amount of time. If they're shut down, they need to be shut down for a very, very small period of time. In that process, if you need to close it for 28 to 90 days to allow concrete to cure, is basically a dead end over there. It's not going to happen. So PCPs are very, very attractive for airport runways because you can shut them for a couple of hours, lay these precast blocks and immediately open it up. They have full strength and they have superior performance. So finally, after understanding these four different types of pavement, so we looked at JPCP, JRCP, CRCP and PCP. After looking at these four, an obvious question is, which one should you use? If you were a pavement engineer and you had a choice in terms of what to use, what should you use? By far, JPCP is the most commonly used type. It is relatively easy to construct. It performs quite well also. JRCP is rarely used. The performance hasn't been as good in practice, and you still have the issue of joints which you have to saw. So you don't get very good performance. You still have a lot of constructability issues. So they are generally not used in practice. CRCP is an option, and it's a very good option for roads which carry a high volume of heavy traffic. But you have to keep in mind that it is very expensive. So CRCP is very good for heavy traffic. If constructed properly, there is basically very low maintenance. So if it's very crucial that the road should not be closed down, it must be allowed to function at full capacity over decades with very little maintenance, then CRCP becomes a very attractive option, but it's also a very expensive option. Whereas JPCP is lower volume roads, which you can shut down for repairs once in a while. PCP is crucial if you want fast opening times. Airport runways is a very good example. If you need fast opening times and superior quality control, then PCP is a good option. So now what are we going to study in this course? In this course on analysis and design of rigid pavements, almost completely we are going to talk about JPCP, jointed plain concrete pavements. Again, this is because this is the single most widely used type of pavement, and the analysis and design of the other type of pavements is built as a variation of the analysis and design of JPCP. So if you understand how to analyze and design JPCP, it's only minor tweaks required to analyze other types. In particular, we will spend a little bit of time talking about the analysis and design of CRCP, not much, because again, the purpose of steel in CRCP is not to increase the strength. The strength of CRCP, as for design purposes, is the same as the strength of JPCP. The difference is in what we call failure or the crack opening, that changes. So we look at it in terms of the crack performance, not in terms of the strength. So mostly in this class, we will stick to analysis and design of JPCP, which is what I mean by rigid pavements. We'll spend a little bit of time also on CRCP. JRCP is so rarely used, it's really not worth too much time. It's better to understand CRCP than JRCP. And PCP is also rarely used enough, and a lot of PCP analysis actually should come from structural engineering in terms of precasting. So we're not going to talk about that in this class on transportation engineering either. Okay, so that concludes today's lecture. So to summarize, in today's lecture, we went to a lot of detail. First of all, we went through the different layers and the different components of rigid pavements. We saw that rigid pavements are inherently multi-layer structures. Structurally, they need not be. Slab on grade is perfectly fine structurally, but for construction purposes, they are almost always multi-layer structures. And then what we saw is that the different types of rigid pavements basically depends on what that first layer, the rigid pavement layer or the concrete layer, how that first layer is constructed. Whether you have joints, whether you have steel, where are the joints, where is the steel, whether you have precasting or you have cast on site. Based on that, you have these different types of pavements which are constructed, of which, as I mentioned, JPCP is the most important, which we'll focus most of our energies on. CRCP is also important. We'll spend a little bit of time on CRCP also. So that concludes lecture 2. Lecture 3, which will be our next lecture, we're going to talk briefly about the different materials used in rigid pavements. We've spent some amount of time talking about concrete and cement and its different components and a little bit on the hydration process. We'll also look at different materials. In particular, what we look at in lecture 3 is characterization of these different materials. And characterization, we'll see, is inherently dependent on how we analyze the pavements. So we'll also get a little bit of an introduction to rigid pavement analysis and characterization of materials for rigid pavement analysis. That's all for this lecture. Thank you.